Hello, this is Ben Isby with Lab 3. So in Lab 3, we're exploring the magnetic field of a dipole. This dipole is just a simple bar magnet. Using an app on our phone called Firefox, we could use our magnetometer to measure the magnetic field of this bar magnet, and then using the Biot-Savart law, as well as just the formula for the magnetic field of a dipole, we could take some observations, find its magnetic moment, and then using that magnetic moment, we could find the hypothetical magnetic field at a certain distance from the magnet, and we can compare that to our observed distances. So in this, we found our n to be about -2. We found d perpendicular to about 19 centimeters. Our observed magnetic field at 45 degrees was about 6619 -208 microteslas, and this is compared to a hypothetical value of about 7.7, 23.2, and 0 microteslas. So first we found the magnetometer chip in my cell phone. To do this, we first had to orient our phone such that the magnetic north pole was accounted for. This was when the field of the magnetic north pole was about perpendicular to the magnetic field of the dipole. So this should be where the absolute value of the magnetic field in the x direction was about 0, and the net magnetic field was roughly that of the net magnetic field of the Earth at about 49 microtesla. So we did that, and then using the approach in the lab, we found the magnetometer chip in our phone. I found it to be about in the top left corner, as indicated on this red dot in this picture. And looking at the blueprint of my phone online, just to verify, that is indeed where it was. And then from there, to find the magnetic moment, we had to find the certain distances from the magnet where different net values of magnetic fields in the x direction were found, respectively 20, 70, 120, 170, and 220 microteslas. And then, so doing this 3 times and finding the average distance for these different values. For 20, it was at about 40 centimeters. For 70, about 18 centimeters. 120, about 16 centimeters. 170, about 14 centimeters. And 220, about 12 centimeters. And then plugging this into a regression formula such that the net magnetic field of the bar was k r to the n. We found n to be about -2.0261, k to be about 2.9 e to the -6. And using k and r to solve for the magnetic dipole, we found that to be about 3.1. And that's again using the formula for the magnetic dipole shown here. It's important to note we would have expected n to be about -3. The fact that it's about -2 shows there's probably some issues in gathering our data. Maybe there was a computer running nearby that was producing its own magnetic field, or maybe I wasn't able to hold my hand steady, and so it wasn't perfectly negating the net magnetic field of the Earth as I was doing the experiment. And so just to be aware of that is important as we move forward, because there should be some propagation of error. And now to find the hypothetical magnetic field at the distance, we first generated the dipole shown here, and then we generated the magnetic fields both on axis and perpendicular. And then also at D, we generated a magnetic field there. And so putting this all out, you see here's the magnetic field at D, this purple arrow. And D was about 27 centimeters. And again, the magnetic field there is about 7.23.0, hypothetically. And again, that's very different from our observed values. So in conclusion, there's an inverse relationship between the distance between a magnet and the magnetometer and the absolute value of the magnetic field in the x direction. So as you get closer to the magnet, the magnetic field grows stronger, which this makes sense. And then if you took 2 identical magnets and stuck them together, it would generate an even larger magnetic field. This larger magnetic field would lead to larger values of R20, R70, D perpendicular, etc. And then if we had failed to orient for magnetic north, this would have produced poor data, as because Earth's magnetic field would not have been perpendicular to the bar magnet. So then any measurement of the net magnetic field would have had both the magnet itself and the Earth interacting together, and so we wouldn't have just gotten the value generated by the magnet. It is possible that this is why we had such wildly different hypothetical values and observed values, because perhaps I was not holding my phone steady, and so I was not perfectly aligned, and so that could be one source of error. Thank you for your time.